something called the definite integral. And it coincides with something called the fundamental theorem of calculus. And, it's kind of funny. We've been in 2 semesters of calculus, and we're just now getting to, you think about the word fundamental as being the basics. We're just now getting to the fundamental theorem of calculus. But I mentioned before that the antiderivative was actually discovered before the derivative. We just teach it in reverse. So based on that, it should make sense that the fundamental theorem of calculus would come second. So it's something called the definite integral. And the fundamental theorem of calculus says that if you have the integral, and this is read as, we read bottom to top, just like you were taught to read when you were taught to read. We say it's the integral from a to b of f of x dx. Okay. So what the integral from a to b of f of x dx is, it's equal to the function's antiderivative at a subtracted by its antiderivative value at b. Again, that cap f is the notation for antiderivative. Now, in the context of this problem here, when we come to the definite integral, we do not consider the plus c portion of it. Because what's going to happen is in this case, it's the same function, so the c value is going to be consistent. So the c value for the antiderivative at a is equal to the c value of the antiderivative at b. So when you subtract the two, the c's would go away. All right. Now, let's look at this. Let's look at an example here. So we start off with this. Let's say we want to go from 0 to 1 of x squared dx. Well, this would be understood to be x cubed over 3. And then we have this bar there that basically says, hey, we've taken the antiderivative. We don't want this integral symbol in there anymore, but it's still from 0 to 1. Well, we said it was going to be the function's antiderivative at a minus the function's antiderivative at b. So this becomes 1/3 minus 0/3, right? Which is equivalent to 1/3. No, it's not the other way around. I wrote the formula wrong. It's f of b minus f of a. Sorry about that. Did I say a and b? Oh, well, I was incorrect. Thank you, Christine. So it's cap f of b minus cap f of a. All right, now, based on that, I want you to look at your notes from class from last time. And I want you to look at where we did the summation of area from, for f of x equals x squared from 0 to 1. We did it for the left-hand limit using infinite partitions. We did it for the right hand using infinite partitions. And what did we come up with as the answer there? 1/3. Now, what we're going to see from the fundamental theorem of calculus is that the antiderivative is going to have a relationship to the area. Now, you may say, well, that's exactly the same thing, so is it not the same thing? Well, it's not the same thing when we start talking about having some functions. What happened to my... I don't know why it's going into sleep mode. Okay. That got me off track, sorry. But if you think of what we're doing here when we're summing up, we've got the limit as n approaches infinity of b minus a, oh, well, no, let me put that at the end. I equals 1 to n of f of I, which we got, well, what did we say that was going to be? If a is 0, it's b minus a times I over n times b minus a over n. Now, what did b minus a over n represent? The width, the thickness, right? And it became infinitely small. And what did this represent? The heights. Those were the heights of the function, right? So we got all of our areas by saying height times width. Well, what's happening in this antiderivative is, think about when we learned what a derivative was. And when we learned what a derivative was, we were trying to, we said it was the limit as h approached 0 of the limit of f of x plus h minus f of x over h, right? That was the derivative. And this h was this change in x. And that change in x, we were trying to get infinitely small to 0. So basically, we've got these thicknesses, which is represented by the derivative. Those are your thicknesses of each partition times all of the infinite heights of the partitions. So that's how the integral corresponds with the summation. So now, instead of going through all of the summation stuff and doing the limit as n approaches infinity for it, what do we have here to take its place? We have this integral, and it's a lot easier to evaluate the integral of the function than it is to evaluate the summations. Right? Okay. So, especially when we learned last time that 20 minus 1 was what? 39. Very good. So, now there is a little bit of a difference here, and that difference is here. If we go from here to here, and let's say that this has an area of A and this has an area of B, and we're going from, let's say, 0 to 4, I don't know why I'm doing that, but the integral from 0 to 4, and let's just call this function g of x, would equal to the area of A minus the area of B. In other words, why would that be? Why do you think that it would work out instead of being A plus B here? What's the big difference in area A from area B? Yeah, these are all above the x-axis, so represented by positive y values. These are all below the x-axis, so represented by negative y values. So A minus B is what happens there. So it's not entirely the area, but the integral has a direct relationship with the area, or has a relationship with an area. So let me pause.